In this problem, we're going to practice using the calculus of thermodynamics to analyze a liquid system. And so what we have going on here is we have a tank of a water heater that has a volume of 80 liters and is initially full of water at a temperature of 130 degrees Fahrenheit, and that water is at atmospheric pressure, 1 atm. Right, and these water heaters, they're designed to maintain the water at that temperature, but there's a malfunction with the instrument, and unfortunately the heating element remains on, and so heat is continuously being added to the water. And because heat's continuously being added, the temperature of the water is increasing as well. Now, because this tank is like a rigid system, the water can't really expand anywhere. The volume can't change. But as a result of the heat continuously being added to the system and the temperature rising, the pressure of the system is going to continuously increase. But this water heater has a pressure release valve on it that's designed to open when the pressure of the system is equal to 10 atmosphere. And what this problem wants us to figure out is it wants us to figure out at what temperature will that pressure release valve go off. Okay? To help solve this problem, we're given information about the isothermal compressibility and the coefficient of thermal expansion, and those are listed here. Okay? Alright, and so based on this problem description, I want you to pause the video here and draw a schematic of the system. Based on this problem statement, we could draw a schematic that looks like this, where we have our water tank. It's at an initial state where the temperature is 130 degrees Fahrenheit, pressure is 1 atm, and the volume is 80 liters. Now, heat is going to be continuously added to this water, right? And so that causes the temperature to change. But at least for the purposes of this problem, we actually don't really care about the actual value of the heat. Presumably, if you wanted to figure out that Q value, you could do an energy balance. But what we're more interested in is we know that once the pressure of the system gets to 10 atm, the pressure release valve will go off. Okay? And so what we want to figure out is what temperature will that pressure release valve go off at. Okay? Because this is a rigid water tank, the volume of the system is going to be constant. It's going to stay at 80 liters. Okay? So for this problem, we have one unknown, so we just need one equation. And what we're interested in is we're interested to figure out temperature. And we're told information about pressure and volume. And so, since we know P and V, what we want to do is define temperature as a function of pressure, and instead of regular volume, I'm going to call this a molar volume, or we're going to define it in terms of molar volume. Okay? Alright, and so if we're defining temperature as a function of pressure and molar volume, if we write out its total derivative, it would look like this. Okay? Alright, now once again, in this system it's rigid, it's a rigid tank. And so regular volume, like the actual just regular V, is going to be constant. But the system is also a closed system. Mass is not going in or out of the system. So the number of, moles in our system is not going to be changing either. All right? And so if both volume aren't changing and the, mass or the moles in our system aren't changing either, that would mean that the molar volume in our system is also constant. Because remember, molar volume is just regular volume over N, and both of those things are the same, or are constant in this problem. So closed system, no change in moles. Okay. All right. And so if there's no change in molar volume, that means dV is equal to 0. And so this term is going to go away. Oh, I mean, not that term. This term is going to go away. And so what we're left with in our total derivative is that dt is just equal to the partial derivative of temperature with respect to pressure at constant molar volume times dP. Okay? All right, and so if we wanted to figure out T2, we would just have to integrate, and we would get T2 minus T1 on the left-hand side is equal to the integral of dt dP at constant V dP. Okay? All right, so that's at least like the basic approach or basic outline for solving this problem. Okay, so we need to figure out what the dt dP is at constant volume for our water. Now in the problem statement, we're given a couple of properties. Specifically, we're told that alpha V, which by definition is this, we're told that's 2.9 e to the negative 4 inverse Fahrenheit. And kappa T, which is this, dP constant T, that's equal to 4.5 e to the negative 5 inverse atmosphere. Right? So both of these are partial derivatives of volume with respect to either temperature or pressure. But in our total derivative, or at least in the equation that we're trying to solve, we have a partial derivative of temperature with respect to pressure at constant volume. Okay? And so, in order to be able to utilize these parameters, we need to be able to rewrite dt dP at constant V. We need to be able to figure out how we could rewrite it in terms of alpha V and kappa T. Okay? All right? And so essentially, if we take a look at this, all we really want to do is we just kind of want to flip the order of these variables. We want to cycle them through. So instead of having T on top, we either want it in the denominator or we want it in that constant slot. All right? So one mathematical tool that allows us to kind of just flip around these different variables is that triple product rule. So dt dP of constant V, according to the triple product, it would just be this. Okay? All right. So now we have the partial derivative of volume with respect to pressure at constant T over dV dt at constant P. All right. So for this one up here, negative dV dP at constant T, that's basically what we get in the kappa T parameter, right? Except all we do is just move that V to the other side. And then dV dt at constant P, that's our alpha parameter, if we just move volume over here. All right, and so we could rewrite this ratio from the triple product like this. Okay, and these volumes cancel out, and what we're left with is that our dt dP at constant V is just a ratio of these two parameters. Right? And for our system, both of these things are constants. Alright, and so that helps simplify the problem down. So if we go back to our temperature equation, T2 minus T1, what we want to do is we want to integrate dt dp at constant v, and we showed that it's just equal to this. And we're integrating that from P1 to P2. And so since these are constants, we could even just pull them out of the integral. We get pressure 2 minus pressure 1. Okay? Then, in the end, we want to figure out T2. So T2 is just equal to this. And now we just plug and chug. And we find that our water hits a pressure of 10 atm when the temperature just rises not that much, only by 1.5 degrees. Okay. All right, and so in this problem, what we saw is that we could describe how, the temperature the temperature of a liquid changes as both a function of, or as a function of pressure, just by applying the calculus of thermodynamics.